So, welcome to the second week of our conference, and also welcome to the new people who joined this week. As you probably noticed, the first week was slightly more pedagogical in the sense there were some overview lectures and mini courses, and the second week will be primarily on research talks or new results. And so we start this morning with Jason Lotay from Oxford, and he will talk on recent progress in Lagrangian mean curvature flow on surfaces.
Thank you very much. Thanks to the organizers again for inviting me to speak. I'm very pleased to have been the last speaker of the first week and the first speaker of the last week, which is very pleasing symmetry. Okay, so what I'm going to talk about today is about a geometric flow of submanifolds. So it's going to be, the flow equation is going to be, L is going to be a family of submanifolds, H is going to be the mean curvature vector. And the submanifolds I'm going to be talking about are going to be surfaces. So they're going to be two-dimensional submanifolds, and they're going to be living inside a real four-dimensional ambient manifold. And these submanifolds and manifolds are going to be of a special type. My submanifolds are going to be what's called Lagrangian, and the ambient manifolds are going to be labial. So I'll define everything in a minute, but just to give you an overview of what we're going to do, what I want to tell you about is recent progress that we've had in trying to understand the following problem. So suppose that I have an initial surface so the question was, do I ask M to be compact? L to be compact. So I don't demand L to be compact. No. Although for the main applications, you'll want L to be compact. But for what I'm going to say, most of the time, you do not need L to be compact. You do need it to have some kind of good asymptotic behavior at infinity. It can't just be random. But let's imagine that it's compact, and suppose it looks something like this. It's some kind of sphere, and we want to try to minimize its area, because that's what the mean curvature flow does. Okay, that's what this flow is. This is the mean curvature flow. And if we're in a Calabi-Yau manifold, then the mean curvature flow preserves the Lagrangian condition, and so we can talk about Lagrangian mean curvature flow. Okay, so when we have an initial compact surface like this, then we can imagine trying to decrease the area as quickly as possible. And what it will tend to do, if this neck is small enough, then it will want to break up your sphere into two pieces. And so there's a series of conjectures known as the Joyce conjectures, and what they say is that we can find there exists a canonical decomposition of certain compact Lagrangians. Okay, so that's what I want to, so I'm going to fill in the blank there in a bit, but that's the idea, okay? The conjecture says that there exists a canonical decomposition of Lagrangians, and you can realized via the Lagrangian mean curvature flow. So you start off with an initial compact Lagrangian, you run the Lagrangian mean curvature flow, and then it will break it up into some kind of canonical decomposition. Okay? That's the conjecture. So what I want to do is tell you about progress towards understanding these conjectures. Okay, so let me now try to define things a little bit. So the starting point is just suppose that our ambient manifold is just complex Euclidean space, C2, and I have complex coordinates Z1, which is X1 plus I Y1, and Z2, which is X2 plus I Y2. Then I have a bunch of different objects that I know very well on this complex Euclidean space. I've got the Euclidean metric. I've got Euclidean complex structure, that's just multiplication by I. I have the Kähler form, so in coordinates, this is just dx1 plus dy wedge dy1 plus dx2 wedge dy2. And I have what's called the holomorphic volume form. So this is just dz1 wedge dz2. And what you see is because these are constant coefficients, the forms, you see that they're closed. These are closed forms. So what a Calabi-Yau manifold is, Calabi-Yau just says at every point we have exactly the same data. So we have a Riemannian metric, a complex structure, a two form of this type, and a holomorphic volume form with those same two conditions. That the two form is closed and the n form is closed. And the thing that's important about this is that if I look at the holonomy, so the group generated by parallel transport around loops in your Calabi-Yau manifold, then it's going to be contained in SU2. So this is, I'm doing everything in dimension 2, and so this means that the metric is Ricci flat and Kähler. Okay, so that's the ambient geometry that I'm going to be caring about. All right. I should say, if you have any questions, please do stop, interrupt me, and I'll explain. So what are some examples? So you could take M to be the cotangent bundle of S2. That's called the Iguchi-Hansen space. Another example, if you prefer, so that's non-compact. If you prefer compact, then you can take M to be the K3 surface. So what's nice is that both of these have nice compact Lagrangian submanifolds, both of these objects. So what are Lagrangian submanifolds? So L2 contained in M Calabi-Yau is Lagrangian if and only if, when I restrict the two form to L, I get 0. That's the same thing as saying if I take the tangent space to L, any tangent space to L, and hit it with the complex structure, I get the normal space to L. And another way to say it, which is useful for my purposes, is that if I take this holomorphic volume form, omega, and restrict it to L, so this is a complex n form on an n-dimensional submanifold. So here n is 2, so a complex 2 form on a 2-dimensional submanifold. So it's a multiple of the volume form on L. I'm just going to assume that my L is oriented. And it has to have unit size. So it has to be e to the I theta times the volume form on L. All right? So this is all the same. This is all what Lagrangian means. And this e to the I theta, or theta, is called the Lagrangian angle. Now, in general, I've only defined e to the I theta. So that means that theta could be multi-valued. But we say that L is 0 Maslov if and only if theta is single valued. It's not for me, is it? The phone? Right. So a very nice fact about Lagrangian mean curvature flow is that the mean curvature, although it's defined in a purely Riemannian way, no, absolutely not. No. It's a multiple, but the multiple can change. I mean, it's a function. Theta is a real valued function. So i.e. theta is a map from L to R. Yeah. It's a map from L to R. Yeah, definitely not a constant. I mean, you're sort of jumping ahead. I was about to say that constant is obviously a very special case. That's important, right? That's going to be very important, and I'm just going to explain that now. So if I come back to this formula, for Lagrangian mean curvature flow, the mean curvature always has the following form. It can always be written as J, the gradient of the Lagrangian angle. Okay? It can always be written in this way, J gradient Lagrangian angle. So what does this mean? Well, if I want H to be 0, then I need theta to be constant. Exactly as you pointed out, you see that being minimal Lagrangian, so I'll just write it again here, H is J grad theta. Therefore, the critical points of the Lagrangian mean curvature flow exactly correspond to theta equals constant. And this is what is known as special Lagrangian. So I can go back now here and say what the Joyce conjecture says. It says if I have 0 Maslov Lagrangians, compact Lagrangians, so things for which the Lagrangian angle is single valued, well, that requirement that the Lagrangian angle is single valued, that's preserved by the flow. It can't suddenly stop being single valued. It starts single valued, it stays single valued. And that's good because we're trying to make it constant. So if it were multi-valued, there'd be no hope of making it constant at some point. So it'd have to start single valued if I want it to end single valued. And this canonical decomposition, so i.e. L splits into L infinity, which is a union of special Lagrangians. Okay, so that's what it says. It says you start from an initial 0 Maslov Lagrangian compact, you run the Lagrangian mean curvature flow, and then you're supposed to eventually end up with a decomposition, canonical decomposition into special Lagrangian submanifolds. Okay. All right, so let me make some comments about this. So there are lots of challenges involved. So the first thing is that special Lagrangians are area minimizing. So that's very good because we're doing the gradient flow or negative gradient flow for the area. And so the only critical points are absolute minima. So that's good, right? There's no sort of higher order critical points. Everything's a minimum. We should be able to contract down to the minimum. So this is a good thing. So it's going to go a bit like good news, bad news, good news, bad news, a bit like that. So this is good news. Bad news is there's a result of Neves which says the following. For every compact Lagrangian L2, there exists another Lagrangian L prime. And let's say it's zero Maslov as well. Excuse me. Which is also zero Maslov. And L prime is Hamiltonian isotopic to L. So what does that mean? That means that we can relate them. So there's a one-parameter family of Lagrangians starting at L, finishing at L prime, which satisfies an equation that looks like this for functions HS, which are called Hamiltonians. Okay? So the flow that takes you from one Lagrangian to the other is generated by a function. But that function can depend on S, which makes life difficult. Interestingly, that's exactly the same form as what the mean curvature flow looks like, right? It's J gradient of theta, where theta depends on time. So that says that the Lagrangian mean curvature flow is a Hamiltonian isotopy in particular. Okay, so what this means is you should think of the following picture. I start off with some initial Lagrangian L, which maybe is very nice, and then I have some other Lagrangian L prime, which is Hamiltonian isotopic and C0 close to L, such that, and here comes the bad news, Lagrangian mean curvature flow starting at L prime develops a finite time singularity. Okay, so let's just think about that for a minute. What is that saying? That's saying that if I start with any initial condition, even a special Lagrangian, so something that's not moving at all, right? I can start with any Lagrangian, I can perturb it very slightly, and now the flow will have a singularity in finite time. Even if the initial flow is actually a critical point, this will happen. So that means that singularities are very easy to come by. And so when Joyce made this conjecture, he was not suggesting that this would be a flow with no singularities at all. That was not what he was suggesting. He was saying that this flow would have to have singularities that you'd have to pass through. So the key point about this conjecture is trying to understand what happens when we reach those singularities. So while I erase this board, are there any questions? Okay, so now another piece of good news is that these Neves examples can be ruled out if we assume, yeah, go for it. Yep. Yeah, it has to be a Lagrangian. Yeah, Lagrangian. Yeah, L is Lagrangian. Everything in sight. Whenever I write L, it means Lagrangian. Yeah, L for Lagrangian. Whenever you see L, it means Lagrangian. Yeah. So zero Maslov only makes sense for Lagrangian. So that's, yeah, I understand your confusion, yeah. So if I start with any zero Maslov Lagrangian, I can perturb it a little bit, and now there'll be a singularity, no matter what the initial Lagrangian was. But these can be ruled out if we assume that L is almost calibrated, meaning that L prime is also almost calibrated. If I assume that L prime is almost calibrated, then this can't happen, right? If we assume almost calibrated. So what does this mean? i.e., the Lagrangian angle doesn't vary too much. The supremum of theta minus the infimum of theta is strictly less than pi. So this also rules out the following example. The Grim-Reaper curve, which is a translating solution to curve shortening flow times R, rules out the Grim-Reaper curve across R. So this has Lagrangian angle variation exactly pi, and so you can't see that either. Go for it. Ruled out, meaning that that is not almost calibrated. So if I assume that the flow is almost calibrated, then I cannot have this. Yeah, so Hamiltonian isotopy doesn't preserve almost calibrated, but I'm saying if I assume that when I assume that I restrict myself only to almost calibrated Lagrangians, then I cannot get that thing, and I cannot get that L prime. So even if the initial L is almost calibrated, even if it's special Lagrangian, L prime is never almost calibrated. It never is construction. In fact, that's how it works. The construction breaks the almost calibrating condition. It makes it, the variation can get as close as you like to pi, but it's always more than pi. And then that's how his construction works. He can make it as close as he likes to pi, but it's always above. And then that's how you construct it. It's one of the ingredients for how you construct the singularity. All right, now I want to talk about, well, if we're talking about singularities, we want to understand what are the singularity models. So another piece of good news is that there do not exist zero Maslov self-shrinkers. So they don't exist. So that means that those are not singularity models for the flow that we're talking about. And again, Andre Neves showed that at a finite time singularity, of the zero Maslov Lagrangian mean curvature flow, any tangent flow is a union of special Lagrangian cones. Possibly with different angles, okay? But here is where I can use the fact that our Lagrangians are two-dimensional. If we're in dimension 2, that means that these are special Lagrangian planes. So the only special Lagrangian cones in dimension 2 are planes. So this makes my life very easy now, because all I have to do is say, well, if I'm given some planes, what does the singularity look like asymptotic to those planes? Okay, so what that implies is that, so this follows, okay, there's a little bit of work to do, but I'll just put implies that type 2 blowups at finite time singularities will be ancient solutions, in fact, eternal solutions, to the Lagrangian mean curvature flow, asymptotic to unions of special Lagrangian planes. So that's what my singularities are going to look like. Okay. So the simplest case is two planes. Suppose I just have two planes, P1 and P2. Right? In C2. So one possibility is if they intersect at one point and their Lagrangian angles, which I'll just call θ1 and θ2, are the same, then it was shown by Lawler that there exists a special Lagrangian L, which is topologically just S1 times R, so you can think of it like a sort of catenoid. It has two ends, and it's asymptotic to this union. Asymptotic P1 union P2. And there's another important fact that I want to use, is that this L is exact. So what does this mean? This means that if I take the Kähler form on C2, it's a closed form, right? C2 has no cohomology, so it must be D of one form, lambda 0. And then lambda 0, if I restrict it to L, this is going to be a closed one form because omega 0 vanishes on L. This is a closed one form, so it defines a cohomology class in H1 of L, and being exact means that this class is 0, namely that this form is exact. So it's a good name. Okay. Now, suppose that they're not transverse, but they meet along a line. Then it was shown by Joyce, Lee, and Sway that there exists a Lagrangian translator. I.e., so L, which is topologically R2, i.e., LT is the solution to the Lagrangian mean curvature flow is just L plus TV, asymptotic to P1 union P2, and L is exact. Well, I'm not saying anything there. It doesn't have any topology, so it's automatically exact. But what's more interesting is that it's almost calibrated. So just notice, I drew a translator over there. I said that that is not almost calibrated, but these ones are. So somehow you thought that you'd won, you thought you'd got rid of the translators, but in fact you haven't, unfortunately. We still have them. Okay. All right, so here are some models for possible singularities, right? These things, this L is called a Lawler-Neck. And the other thing doesn't have a name, just translating solution. Those are possible singularity models. And so what we want to do is try to understand these singularities. So one of the conjectures due to Joyce is that Lawler-Neck singularities, so we might call it Lawler-Neck pinch singularities, are generic. So this conjecture is quite vague. I'm not going to define what I mean by generic, but one way you could define it is saying, suppose that a Lawler-Neck singularity forms. I perturb my initial condition a little bit. A Lawler-Neck singularity is still going to form. That would be a definition of what I mean. Okay? So now I can finally state first theorem. This is joint work with Felix Schulze and Gabor Zekelahidi. And it says the following. So suppose L is exact. That's right. So, and almost calibrated Lagrangian mean curvature flow. So let me drop this for now and just say plus a topological assumption that I don't want to explain. L is almost calibrated Lagrangian mean curvature flow with finite time singularity. Where one tangent flow is a union of two planes which meet at one point. Okay. So that's my assumption. I assume that I have at least one tangent flow. So I should have said that here. So I tried to, I sort of hinted it when I wrote this. I wrote any, right? I wrote any tangent flow because the tangent flow need not be unique. Okay, there could be lots of them. But so all I know is that at least one of them is a pair of planes meeting at one point. Then what the theorem says is that I know exactly what is happening at the singularity. So what am I doing? I'm taking just this first order information, just the tangent flow, that's just a pair of planes, and now I'm going to tell you is exactly what the singularity must look like. Right? So I'm going to start from just that information and then say what the singularity must look like. Yep. Yeah, go for it. Yes. Yep. So because it's almost calibrated, that means it's in particular zero Maslov, right? Because the angle varies less than pi, so in particular it's single valued. Yeah. So almost calibrated is stronger than zero Maslov. Yeah. That's a good question. Okay, so what can we say? We can say that the following. We can say that the Lagrangian angles actually have to be the same for the two planes. Okay? It's the first thing that you can say. So I didn't assume that, right? I just said it was just a pair of planes that met at some point. I know that they actually have to have the same angle And I know that a Lawler neck. Oh, yeah, that's what I'm going to say. The tangent flow is unique. So in fact, even though I said it could have been possible, there were lots of them. In fact, there's only one. And a Lawler neck pinch occurs. We can actually say more. We can say that at the singular time, t, the flow LT is actually still C1 and is immersed. And that means that, therefore, we can continue the Lagrangian mean curvature flow past time t as an almost calibrated. Okay, so what we can do is we have our Lagrangian that looks like that. So in the usual mean curvature flow, what you would see is a bunch of cylinders shrinking. But here what we see instead is like these hyperboloids shrinking down. Something like this, till eventually it becomes schematically a cone, but it's a pair of planes. So that's what happens, right? And when that happens, what I'm saying is that you exactly get the picture that I had at the start. You get an immersed submanifold. Does it make sense, what I've drawn? It's just the usual picture. I mean, this is just a cartoon, but it's suggestive. It's just how a hyperboloid of one sheet becomes a cone, right? It's the same sort of procedure. You shrink down the Lawler necks, they become a pair of planes, and that's exactly the model, pair of transverse planes, and that's exactly the model for an immersed double point. So that's what happens. All right, any questions about this? All right, but that's an abstract result, right? It just says, you know, suppose that this happens, suppose I know I have the situation, then I know what to do with the flow, right? But could you ever use it in practice? Is there ever a time when you can actually satisfy the conditions of this theorem? Maybe it's an empty theorem and I've wasted your time. No, it's not, okay. Let me tell you this. So let me say the following. So now there's a very important fact I'll tell you is that there exist infinitely many topological types of S1 invariant Calabi-Yau M. So I'm going to put M4 just to say that, I mean, they're complex two-dimensional, but they're real four-dimensional, which contain infinitely many compact, almost calibrated exact Lagrangian. Well, because they're surfaces, I mean, then in fact they have to be S2s. So they exactly, it's the picture that I drew. They're spheres, right? They look a bit like what I was drawing there, in fact. So we have lots and lots and lots of these, and these are given by, so this is just words, but in case you've, so these are given by what's known as the Gibbons-Hawking ansatz. Oh, I missed out one important thing. They're also S1 invariant. Because, yeah. Gibbons-Hawking ansatz. So, okay, so it means two different things. So first of all, that the manifold has a global S1 action that preserves everything. So the metric, complex structure, little omega, big omega, everything is preserved by that S1 action. That's what this S1 invariance means. This S1 invariance means is that circle action preserves the Lagrangian as well. Right? But this circle action is not free. It can have fixed points. And that's actually very important. Otherwise, you couldn't have got an S2, of course. It must have fixed points. And that's actually the important fact. So just for it, what they look like, so what they look like is T star S2 is an example of such a thing. So the Iguchi-Hansen thing that I wrote down. And more generally, you can take C2 quotiented out by a cyclic group action and resolve it. So if you know about these things, then this is great. If you don't worry about it. But this is how you can see K can be any number, any integer, any number starting from, yeah, well, okay, not zero. And so this gives you the infinitely many different topological types. Okay. All right, and so what can you do in this setting is you can prove the following result. You can say that this theorem that I just wrote down over there on the right applies. And so what the theorem says is the following. So this is joint work with Gonzalo Oliveira. And what it says is that given any compact S1 invariant, almost calibrated S2 in examples above, there exists a continuous, let's call it L, this continuous family LT, T is in 0 to infinity, with L0 equals L, and 0 less than T1 less than TL less than infinity. So what are these going to be? These are going to be the finite number of singular times. That's what they're going to be. Such that so for T not equal to Tj, LT satisfies the Lagrangian mean curvature flow. At T equals Tj, Lorentz pinch occurs. And then as T tends to infinity, L tends to L infinity, which is a union of special Lagrangian submanifolds. And in fact, L and L infinity are Hamiltonian isotopic. That's all right, isn't it? Because that's what we wanted. We wanted to break up an initial Lagrangian into a union of special Lagrangians. So that's good. Okay. Any questions about that? Statement clear? So I should come clean. I mean, this is very nice. I mean, I'm not going to say it's not nice, but I am going to say that, of course, I haven't proved this decomposition is canonical. Right? This doesn't resolve the conjecture completely because I haven't said that the decomposition is the one, the canonical one. I've proved there's some decomposition into special Lagrangians. That's what I've proved, which can be realized via the flow. That's what I'm saying. Right. Yep. Yes. No. So in this setting, the only topology you can get is S2 if you want almost calibrated. If you want just S1 invariant Lagrangian, you can also get tori and you can get cylinders, but you cannot get, if you want it to be compact and almost calibrated, the only thing you can do is a sphere. The only thing. Yeah, that's just for our theorem, but I mean, of course, you don't really want S1 invariant, you want to get rid of that. Then you can have anything. So if you get rid of S1 invariant, then you can have anything, I would imagine. But then you can get high genus for sure. Yeah. But for this situation, yeah, you cannot. Okay, so that deals with the case where the planes were transverse. So what happens if the planes meet along a line? Right? That was the other option that I said could happen. And we would get a translator in that case. Well, we saw that we could get a translator in that case. That was an option of something that could happen. And so there's a conjecture due to Joyce again that says that the Joyce-Lee-Sway translators give generic singularities. Well, let me say it more like this. Let me not say that. Let me just say that P1 union P2 with P1 intersect P2 is a line, gives generic singularity tangent flow. Okay, so what it says is, suppose I have some flow that shows that I do the tangent flow and I see two planes meeting along a line, then when I perturb things a bit, I'm still going to see that. That seems a bit strange because if you have two planes in 4 dimensions that are 2-dimensional, they should only meet in points, really, generically. Meeting along a line does not seem very generic, and so it isn't, for sure, amongst planes, but what Joyce is saying is that if you, for the flow, you can't perturb that away. So once you see it, at some time you perturb it, you're still going to see it. Okay. All right, and so what is the theorem in this situation? So this now is again with Schulze and Sekulahidi. It says that let LT So everything's two-dimensional, B, almost calibrated, exact. Ancient solution, asymptotic to a pair of planes with P1 intersect P2 is the span of V. Then, well, what? I mean, that's not very much information, right? I've got some random ancient solution, and at infinity, it looks like a pair of planes meeting along a line. The only thing in my favor is that I know that there is an ancient solution that looks like that, namely a translating solution, right? The Joyce-Lee-Sway translators. So I might hope that I can prove that this thing is a translator, and indeed it is. So, is a translator. So I cannot prove that it's the Joyce-Lee-Sway translator, but what I can prove is that it is a translator. Okay? So initially it could have been anything, but now it has to be a translating solution. So that means we can focus our attention on just the translating solution case. Any questions about that? Yeah. Yeah, so in the neck pinch, you see the angle is constant. So in fact, the angle functions just go through, it's nicely. So everything just goes through smoothly, I mean, through the, well, at least continuously through the singularity. Yeah, so that's why I erased it. But I said that it continues an almost calibrated Lagrangian mean curvature flow, and the angle goes through continuously through the singular time. You don't lose angle or something like that. It doesn't jump. So there are other solutions where you could do that, but I think that you would consider to be a bad way to solve the singularity problem. There's nothing about uniqueness. Once you hit a singularity, there's not, in general, a unique flow that will come out. But this flow that we construct, it will at least, the angle will vary continuously through the singularity, which is good for us. Okay, so I think I will finish by asking a question and answering it, which is, so I said that the simplest case for the singularities is when we have two planes, right? And I said that the possibilities were two planes meeting at a point or two planes meeting along a line, but I lied a little bit because you could just have the same plane twice. Right? You could have the same plane twice. So what if the tangent flow is 2 times one plane? And then the theorem is the following. And this is now with Ben Lambert, myself, and Felix Schultzer again, and says that if LT is an exact, almost calibrated ancient solution, asymptotic to 2 times the same plane, then LT is L, special Lagrangian, and L is the same thing as the graph of the map Z goes to Z squared, such that Z is in C. So it's topologically R2, it's just the graph of the map Z goes to Z squared. This thing, you can see, its asymptotic is the same plane twice, and this, in fact, is what it has to be if you have a multiplicity 2 plane. In dimension 2, right? Everything is two-dimensional. Okay, so I think with that we have quite a complete understanding, at least of the local behavior of the Lagrangian mean curvature flow for surfaces near the singularity types that we expect to be the most common. Right? 2 planes is the most obvious. Higher number of planes, you should be able to get rid of those, you would hope, sort of generically push them away. But whenever you see 2 planes, we at least now know what it looks like. And in some nice cases, we can show that the flow does indeed exist for all time through a finite number of singularities and decompose your Lagrangian into special Lagrangians, as you'd hope. And with that, I'll stop. Thank you very much.
Thank you, Jason. So let's move on to questions. Any questions from the audience?
Thank you. So in the Joyce conjecture, is there any information or guess about how the special Lagrangian pieces are intersecting? In the examples you drew, you just had 2 spheres and then they had a kind of this cone point where they meet.
Yeah, yeah. No, there's nothing in that. Yeah, so that it doesn't say anything about the way that they're intersecting. So in our case, what we get, actually in the example that I drew, and in all the cases, it's going to be a chain of spheres. That's what this union is going to be. So it's just going to be one sphere meeting another sphere, which meets another sphere, and so on, just in one point, like that. So that's what we always see in the examples. But in principle, it could be a lot more complicated than that. Yeah, but you would hope that it would just be special Lagrangians meeting at a point, each of them meeting at one point, or a finite number of points. Yeah. That's what, but no, it doesn't say anything about that. The conjecture is, it's expressed in, I would say, vague terms, but they're very inspirational. It's not like it's just waffle. It says a lot of things that are precise, but the exact conclusion is somewhat vague because it's not clear what you might hope to actually prove. I think in dimension 2, it should just be meeting along points, but in higher dimensions, it could be more complicated. So that's actually all that can happen. Special Lagrangians can only meet at points in dimension 2. So it's easy in that case.
Zoomland question.
Hi, Rob. Yep.
Hi, Rob. So,
Yeah,
yes, Rob, you can go ahead.
2 parts. Following up on the previous question, was that Parker, by the way? I couldn't tell from Zoomland.
That was Parker. Yeah, it was Parker. Yeah.
Great. Hi, Parker. I thought the question also had a geometric part, which was where the components meet, whether it's a point. Let's do the 2-dimensional case. Is there anything special about the union of 2 planes or multiplicity planes that you get that are 10?
Oh,
nothing.
Well, I mean, so everything should be multiplicity 1 planes, and but they could have the same angle or they could have different angle. So you could have 2. So, I mean, just sort of cartoonishly, you could imagine. I don't know if you can see what I'm about to draw, but you could imagine that you have exactly the picture that I had. So you had the 2 spheres meeting like this, where then these planes sort of have the same angle, but you could also have them meeting kind of like that, where now the planes have different angles. That somehow, yeah, you don't know. It could be anything. And in fact, in our examples, we show you can get anything. So any pair of angles is possible.
So that was the follow-up to Parker's question. The question I had actually is maybe more elementary. In your statement of the theorem with Felix and I forget who the other person was, there was an equivalent symbol, equals with a tilde over it. Just I missed in what sense it's equivalent to ZZ squared.
Oh yeah, right, yeah, very good. No, you didn't miss it. I didn't say. Yeah, but thank you for asking, because I didn't explain what I mean by this. So what I mean by this is, so of course, this is not saying much. I mean, if I just said it was a bijection or something, that would not be very interesting. What I mean is that I can change the Calabi-Yau structure on C2 so that the Lagrangian becomes this complex curve.
Okay, so it's like an orthogonal.
So in fact, as a set, it's the same. So literally, it's the same set of points as z goes to z squared, but it's just that I'm viewing it differently with respect to the complex structure.
Okay, thank you. Thank you.
Yeah.
Rukmini?
Oh yeah, please, I like those.
So LTs, supposing they have their own symplectic form to begin with.
Which ones?
The LTs.
Well, the LTs, the symplectic form would be 0 on them. Yeah.
No, the ambient symplectic form, but their own particular symplectic form, like as Riemann surfaces, they have symplectic form.
Oh, I see. Yeah. So you're thinking, you're sort of flipping, that's a bit like this. You're flipping the complex structure. Yeah. Mm-hmm.
Right. So what happens to, as it goes down, what happens to that?
Yeah, so that's right. So yeah, so the complex structure is degenerating. So it's exactly like you imagine in Riemann surface theory, how a node develops. You should think of it like that. Like it's like you're taking some Riemann surface and you're building a nodal Riemann surface at the end. Yeah. So that's what's actually happening as Riemann surfaces. The complex structure degenerates at those points. Yeah. So that's what happens to the symplectic form.
More questions?
Okay, so in there, if you drop the assumption of S1 invariance, but you work it in, but you work with an K3 surface so that it's still compact and there's still some restriction. So, will the almost calibrated exact Lagrangian surfaces still be spheres?
We don't know that they have to be spheres. No, they don't have to be spheres. No, we don't know that for sure, but they probably will be. Yeah, I mean, almost calibrated is quite a strong condition. So they may well still be spheres. Oh no. What am I talking about? No, they don't have to be. No, they can be higher genus. No, they can definitely be higher genus. Yes. Sorry. Yeah. No, they can definitely be higher genus. In fact. Yeah. If you drop S1 invariance, then you can. There's many different things. Because the reason is because, as is sort of alluding to the same question that Rob asked, here in a K3 surface, just like in C2, you can flip the complex structure. And so what will happen is that all the special Lagrangians, they'll become complex curves. And of course, you can have high genus complex curves inside a K3 surface. So they would in particular be almost calibrated. And then you could wiggle those a bit and they would be compact Lagrangians, which would be almost calibrated. But exact doesn't make any sense because you can't have an exact symplectic form on a compact manifold. So that's why I wrote this theorem at some point where I said plus topological assumptions, which I don't want to explain. There is a notion that's a bit like exact, which makes sense even when the manifold is compact. So our result still works in compact manifolds as well, but it would take me a little bit long to explain, so I didn't. But there's sort of a notion that's a bit, the notion is, it's basically a restriction on the first homology of the Lagrangian. So once you know something about with integer coefficients, once you know something about the integral first homology of your Lagrangian, then you can prove that any type 2 blowup would have to be exact. And then you can apply the result. The result is a local result. But you can get into that situation by imposing a natural assumption, which can also be thought about some restriction on the holonomy of a flat connection on a particular bundle over the Lagrangian. But anyway, it's a slightly lengthy story, so I will not do it. Yeah. But no, it's super interesting. So in fact, I should say that one of my PhD students is working on exactly the sort of thing that you're suggesting is, well, related to what you're suggesting, is to try to extend this theorem, or at least versions of this theorem, to the case where the manifold is a K3 surface. So and so now you don't have S1 invariance anymore, but can you still find at least examples of compact, almost calibrated things which are not just special Lagrangian, for which the flow will decompose? It is hyperkähler. Yeah, so everything in sight is hyperkähler. So a Calabi-Yau manifold in dimension 2, so when it's a real 4-dimensional, is always hyperkähler. That's because I said the holonomy was contained in SU2, but SU2 is SP1. So that means that they're all hyperkähler. Yeah. But I'm not thinking of them as hyperkähler, but they are. They're all hyperkähler. That's right. And in fact, I should have said, I didn't mention proofs at all, but a lot of the, as you can guess, perhaps from the way this is stated, a lot of the proofs use the fact that everything is hyperkähler. That is actually very crucial in the proof. That's why this entire talk was about surfaces. It wasn't because I'm restricting the topology particularly, but it's because I can flip the complex structure, and so I can think of special Lagrangians as complex curves, and that turns out to be very, very useful. That's really what makes all of the results work, except for the result about translators actually has nothing to do with dimension 2. So that result extends to all dimensions. So the result about translators is true in all dimensions, but everything else is very much two-dimensional because it uses the hyperkähler structure.
Can I ask you another question, actually?
Yeah, sure, Rob.
It's a little bit out there.
I would expect nothing less. Go for it.
Ha ha ha. It's also nearly 2 o'clock in the morning where I am. So
yeah, right.
So I mean, just for surfaces in a Kähler surface, or Calabi-Yau surface. I mean, the Lagrangian mean curvature flow behaves a lot more like a codimension 1 flow because you're Lagrangian. But does it make any sense that, I mean, it was actually one of the earlier questions, maybe it was Rukmini's question, that you answered, that you could sort of flip or turn the most complex structure. Obviously, mean curvature flow works in higher, it's not well understood in higher codimensions. So if one had an isotropic surface, say in a threefold, is there anything at all? I mean, this is, like I said, it's kind of out there, blue sky. Is there anything interesting about the behavior of that? I mean, it's you know, for example, well, just ordinary curve shortening in R3 even is much more complicated than,
yes.
Than it, yeah. Go ahead.
Yeah. So one thing that I can say, I think I can say two things that are related to your question. So one thing that people have studied is, suppose that you have a submanifold on which, instead of the symplectic form restricting to be 0, it restricts to be symplectic again. So it's restricted to be non-degenerate. So you could do this, and this works okay in dimension 4. So again, when you're dealing with surfaces. But it doesn't seem to work that well in higher dimensions. Pointing more to your question directly, so
isotropic case. So
yeah, so I thought about with Tommaso Piccini, I thought about these totally real submanifolds. So when the J of the tangent space is transverse to the tangent space, so not necessarily orthogonal, and you can define a generalization of mean curvature flow, which then preserves the totally real condition in a good way. I mean, it's always preserved by mean curvature flow because it's an open condition, but you can set it up so it looks like a codimension 1 flow again. So it's generated by an angle function, just like the Lagrangian mean curvature flow is.
Okay. So this is in the half-dimensional case, though. Okay.
That's in any dimension, yeah. That's in higher dimensions. You can do a totally real flow, if you like. So we call this the Maslov flow.
But they're half-dimensional. I mean,
they're half-dimensional. They're half-dimensional, yeah. Yeah, so I don't know about isotropic, coisotropic. This I don't know. I don't know what you can do in that case. Yeah.
Thanks.
I have a simple question perhaps. How much of Calabi-Yau do you use? And wouldn't you just, in a Kähler manifold, for instance, you could?
Right, so we do, so what's important for us is that we have this Lagrangian angle. And the Lagrangian angle is a priori only well-defined in a Calabi-Yau manifold. However, you can get around that. So suppose you're working in a Kähler-Einstein manifold more generally. So in all Kähler-Einstein manifolds, the Lagrangian condition is preserved, so you could try to do the same thing. Locally, of course, it's just Euclidean space, so a lot of the local theory goes through. So that's the same, there's no difference. But the flow itself is not a Hamiltonian isotopy in general, it's just a Lagrangian isotopy, so you don't have the same control. However, if you know that your Lagrangian is, say, suppose we take, just to make everything concrete, suppose I do everything in CP2, for example. Then if I know that my Lagrangian always stays away from the divisor at infinity, then I can remove it, and then it's now Calabi-Yau. And so now I can define the angle function, and now everything works exactly as it was. And this is a general trick that, in fact, symplectic geometers use a lot, is that if you have a symplectic manifold, you have a Kähler manifold, you can cut something out, a divisor typically, and then you get something that has first Chern class 0 now, and so now it's Calabi-Yau. And then you have an angle function. Another trick you can do is you can say, well, actually, to define the angle, all I need is one reference Lagrangian, a special Lagrangian ideally, and then everything I should just measure relative to that, and so you can define a relative Lagrangian angle. So then again, you can make it work that way. So the short answer to your question is a lot of it extends. Yeah. It's not really using the Calabi-Yau very strongly in the end.
Okay, thanks. Since there seem to be no more questions, let's thank Jason again.
Thanks.